Imagine a world where a single video, just one sequence of frames, can be used to reconstruct not just the 3D shape of a scene, but its full evolution over time. Every moving object, every changing surface, every trajectory traced through space and time. That's the promise of 4D reconstruction, modeling the world not just as a static structure, but as a living, breathing, dynamic entity. Until now, most approaches to 4D reconstruction have been fragmented. Some estimate camera motion first, then reconstruct geometry. Others predict sparse point tracks, or only model motion between two frames. These methods are either slow, limited in scope, or require iterative optimization after inference, breaking the dream of real-time, end-to-end perception. Enter 4RC, a unified, feed-forward framework for complete 4D reconstruction from monocular videos. Pronounced ARC, 4RC stands for 4D reconstruction via conditional querying anytime and anywhere. It's not just another model, it's a paradigm shift. At its core, 4RC learns a compact, holistic 4D latent representation of an entire video in a single forward pass. Once encoded, this representation becomes a centralized spatio-temporal memory, a unified scene model that can be queried at any time, from any viewpoint, for any target timestamp. Let's break this down. Instead of predicting a full 3D point cloud for every frame, which would be computationally prohibitive and redundant, 4RC uses a minimally factorized representation. Each frame is decomposed into two components. 1. A viewpoint invariant-based geometry, the static 3D structure observed in a given frame. 2. A time-dependent relative motion field, the 3D displacement of points from that frame to any other time. This means, once the base geometry is known, motion becomes a simple displacement prediction. No need to re-reconstruct the entire scene at each time step. This factorization enables temporal consistency, reduces redundancy, and makes the model both efficient and expressive. How does it work? The input is a monocular video, a sequence of RGB frames. These frames are patchified and augmented with two key conditioning signals, camera tokens and time tokens. The camera tokens encode the camera's intrinsic and extrinsic parameters, while the time tokens capture temporal context for each frame. These tokens are fed into a vision transformer backbone, a plain VI-T architecture, but enhanced with a novel design, alternating frame-wise and global self-attention. The result? A compact, unified 4D latent representation, a single spatio-temporal embedding that captures the entire video's geometry and motion dynamics. Now comes the magic, the conditional decoder. This decoder is where flexibility shines. Given any query frame, say, frame I, and any target timestamp tau, the decoder can instantly retrieve the 3D point map of that frame at time tau. It does this through a disentangled architecture, a geometry head and a motion head. The geometry head decodes the base 3D structure from the query frame's latent features and camera token. It predicts depth, rays, and camera parameters, all under the perspective projection model, to reconstruct the static geometry in world coordinates. The motion head, meanwhile, is designed for dynamic queries. It takes the query frame's latent features, conditions on the target time via an AdaLN, adaptive layer normalization, module, and performs cross-attention over the target frame's latent features. This allows it to learn how points move from the source frame to the target, even across large temporal gaps. The output? A dense 3D displacement field, a vector field that tells you exactly where every point in the source frame moves by time. Combine that with the base geometry, and you get a full 3D reconstruction at any timestamp. And the best part? This entire process is feed-forward, end-to-end, and unified. No post-hoc optimization. No multi-stage pipelines. No tracking heuristics. Just one model, one pass, infinite queries. But how does it perform? Extensive experiments on standard benchmarks, including TUM Dynamics, ScanNet, 7 Scenes, Sintel, and Waymo, show that 4RC consistently outperforms prior and concurrent methods across a wide range of 4D reconstruction tasks. Camera pose estimation. It achieves state-of-the-art accuracy, even beating specialized 3D reconstruction models like Pi3, despite being trained on a smaller dataset. Multi-view 3D reconstruction. It surpasses all 4D methods in accuracy, completeness, and normal consistency. Video depth prediction. It matches top-performing methods on Bon and Sintel, with a delta 1.25 score of over 97%. 3D point tracking. On dense tracking tasks, it achieves 85.44% APD on Kubrick and 56.63% APD on Waymo, a 36% gain over V-DPM, the previous best, while using a much more efficient per-frame decoding scheme. Sparse point tracking. It performs strongly even against tracking-specific methods like Co-Tracker 3 and Spatial Tracker V2, showing that its unified representation is powerful enough to capture both dense and sparse motion. Why is this possible? Because 4RC doesn't just predict motion. It learns a semantic, consistent, and queryable 4D world model. It can answer questions like, where will the car be in 10 seconds? What does the scene look like at frame 15, given the geometry from frame 3? How did the person's hand move during the jump? And it does so without reprocessing the entire video. To push further, the authors also introduce S4RC, a streaming variant for online causal inference. This version uses a causal attention mechanism, enabling real-time 4D reconstruction as frames arrive, crucial for robotics, egocentric understanding, and AR/VR applications. But no model is perfect. 4RC still struggles with extreme depth, like distant clouds, transparent objects, and highly chaotic motion, areas where geometric ambiguity is high. However, these limitations are not inherent to the framework, but rather to the current state of depth estimation and motion supervision in training data. As datasets grow and models improve, so will 4RC. So what does 4RC mean for the future of visual perception? It represents a crucial step toward general-purpose, unified perception systems. Instead of building separate models for depth, tracking, pose, and motion, we can now train a single network to reason about geometry and dynamics together, in a single, flexible, and efficient representation. This isn't just about better reconstruction. It's about enabling autonomous agents that understand not just what is in the world, but how it moves, when it will be there, and what it will become. From robotics and navigation to video synthesis and virtual production, 4RC opens the door to a new era of intelligent, dynamic scene understanding. In short, 4RC isn't just reconstructing 4D scenes, it's reconstructing the future, one query at a time.